Hi, my name is John McMaster here in my Silicon Valley lab.
Hey, and I'm Yusuf, and we are Geek Moniker. So this week, you said we're going to be repairing a high-power laser, John, and that's all I know about it. So how about you give us a little intro on what you're gonna cover this episode?
Sure, do you remember a while back we talked about my laser probe station? Do you remember what was the idea behind that instrument and how did it work?
Yeah, so when you're trying to probe little traces on chips, there are multiple layers. So sometimes you need to zap your way through the layers to get to the layer you want to actually probe, and
That's
you use the laser for that.
that's right. Yes, there's a thin oxide layer on top of the chip which is non-conductive. In order to get the little microneedles down, we need to blow off that oxide layer. And to do that, you use a very, very high power laser that ablates the surface instead of cutting it. Do you know ablation versus kind of normal laser cutting?
No. How about you give us a little intro on that?
Yeah, so if you use like a CO2 laser, maybe it's like 40 watt or something, and you're like, oh, high power, which is cool. This layer is a different type, and it's so-called Q-switched, or uses a Pockle cell. And the energy is relatively small, say maybe 30 millijoules, but it does it in a very, very, very short amount of time, such that the power level is actually in the hundreds of kilowatts, but for a very short amount of time. And because of that, instead of melting the material, it actually basically just vaporizes it and ejects it. So the material that you hit is removed and nothing else around it is heated. And this allows you to knock out very specific parts of the circuit without damaging the surrounding area.
Oh, that's cool because I've done a bunch of laser cutting on acrylic and wood, and it definitely does leave burn marks along the path of the laser.
Have you by chance ever used a fiber laser? Because I think they're relatively similar to this.
No, I think they were CO2 lasers.
Sure. Well, in any case, so that aside, one of the issues, though, is these lasers are notoriously unreliable. So Chris Gerlinski, for example, I know has a few of these lasers. I have basically a couple of them here now, and they keep getting sick and dying. So I had this whole quest where I keep trying to figure out how to fix these and what dies in a laser. So let me ask you, what do you think can go wrong in a laser? Do you know much about kind of how lasers typically operate?
Well, I mean, they're high power machines, right? So, I guess things wear out. Like generally in a CO2 laser, you're flashing a whole bunch of light. It bounces around a little ruby rod and pops out one end, right?
Well, CO2 gas cavity in that case, yes. Now, talking about that bouncing, they talk about the gain of the laser. So you have kind of two mirrors. Now, those mirrors have to be very precisely aligned, right?
Yep.
And so that's one problem. And you mentioned the high power. You also can get, dirt, debris in there and stuff like that, right?
Mm-hmm.
So those are the two major classes of things for high power laser. But this laser is even a little bit more complicated because it has these optical switches. So I think maybe this is a good point then. I'm going to switch over to the second camera. We'll actually go through a little bit more about how this laser works.
Sounds cool.
Okay, so now you can see the laser a little bit here. So let's talk a little bit about it. So first thing is, you talked about a CO2 laser. Do you know roughly, you've got a high voltage power supply and it excites some gas, right? And that's kind of in the laser path itself.
Yep.
Yeah, roughly. Okay. And it's got the mirrors. So this laser works completely differently. So instead of having a gas discharge like a CO2 laser, maybe I can see if I can point over here. So this area here, if you can, I think I can see my fingers there. There is actually a high power flash lamp in here. So that's what this red and this black is. A high voltage capacitor off screen stores a lot of energy and then dumps it into a glass flash lamp that's in there, just like a camera. And a high voltage pulse is applied to fire that lamp. And when that happens, this lights up very brightly, and there are mirrors that attach that to a laser rod over here. And that laser rod is made of a material called Nd:YAG, that is neodymium YAG. And that basically fluoresces at 1064 nanometers once that high power flash lamp hits it. Does that make sense?
Yep.
Okay, so that's the first stage. Now, if you did that and you just had one mirror out here, they call the output coupler, I should say this one. If you just had the output coupler, and then you have another mirror called the high reflector, and the high reflector is completely reflective, and the output coupler is semi-reflective, And that allows you to get the so-called gain of the laser. It has to get enough recombinations to actually get a beam out. If you did that, you would get a pulse length that is roughly equal to the length of the flash lamp, right? Because as the flash lamp is going, it says it's keep pumping the laser rod, so you'll keep getting more light out. Does that make sense?
Yep.
Okay, but that flash lamp pulse is relatively long. So what you want to do instead is, this right here is an optical switch, something called a Optical cell. And what that's going to basically do, I'm going to oversimplify and then we'll go into a little more detail. What it's basically going to do is block the optical path. And what's going to happen is, because there's no high reflector mirror, which is allowing the laser to amplify, what's going to happen instead is this laser rod is just going to charge up. So it's going to keep getting saturated with more and more energy. But because the gain, the feedback loop of the laser has been disabled, it's not going to actually laze. So it's almost like a capacitor. Think of it like an optical capacitor. It just keeps building up energy. At some point, though, we're going to apply a high voltage pulse, which is delivered by this board here. And that's basically going to turn this optical switch on, and then it's going to dump an extremely fast, very high power laser pulse out the side of the laser over here. Does that make sense so far?
It does. Now, this definitely sounds like something that happens in the movies. You charge up your laser, you fire it, right? The death ray.
Yes. It's like the Death Star.
So how frequently can it do these pulses? Like, is it just, it takes a whole lot of time and you get one pulse, or does it do it real fast?
Sure. There are a few different models of this laser. Some of them have liquid cooling. If you look very carefully on mine, and I don't think you can see it on camera, there are some water inlets that do allow you to liquid cool this laser assembly over here. I do not have the liquid cooled version. Mine has a relatively limited repeat rate. I'm going to say on the order of 1 shot per second, something like that. You also can do a rapid fire mode, which is extremely satisfying, by the way. But other than that, because it doesn't have a good cooling system and the efficiency is rather poor, yeah, you're limited to maybe 1 shot a second or something like that.
Okay, and generally, how many shots do you need to get through, the layers of a chip?
Yeah, so it's basically, you want to do it exactly right the first time. So it should be 1 shot, because you basically want to excite it just enough to knock off the oxide, but not so much that you actually blast through the metal below. And so it's a little bit tricky to get that exactly right. And that could be a whole video in itself. So I'm going to suggest that we kind of glaze over that application bit right now.
Sounds good.
Okay. So I also encourage you to check on YouTube if there are any comments, kind of while we're doing this, if you are able to.
Oh yeah, we got a couple of icons from live streamers right now, and if any of our listeners do have questions, please put them in. We're looking at the comments.
Cool. Okay, so let's move on a bit. So I oversimplified the optical switch element, and that's where things start getting really interesting. So let's talk about a few other elements. So you may notice that there's this little wedge right here, this angled piece of glass. Can you see that?
Yep.
Okay, I can also try to move this closer if that's hard to see on the feed. In fact, let me see if I can do that. Hopefully this won't end terribly, but let's just try to get at least briefly a little bit closer on this section, because this is going to be important. Maybe I can stack something over here, if you bear with me. Maybe we can try to get something a little bit nicer-ish. I think that's probably the best I'm going to do right now. Okay, so let's talk about this section right here. And hopefully I can balance this, but maybe not. All right, so what we've got on the left, that little angle bit, is what's called a Brewster window. Have you ever heard of that by chance?
No.
And yeah, maybe there's some wires there that are kind of blocking that. But anyways, yeah, that guy right there. And the basic idea is you can, and this is not a strong area of mine, so please don't ask for details, is you can polarize light if you put things at just the right angle. So just for the purpose of our arguments, let's just say that that's a polarizer right there. And are you familiar with beam polarization and like optics?
Somewhat.
Somewhat, yeah. So high level idea is, and because this will be important for purposes of our discussion, let me get this camera back up here so it's stable, hopefully. Stand by, maybe. Okay, I think that's stable enough. So yeah, for the purposes of our discussion, there's polarization of light. If you're pointed one direction, the light will pass. If you're pointed in not the direction we're currently polarized, the light will not pass. So it has to be, going, say, vertical or horizontal. And if horizontal hits vertical, the light will not pass. So this will put the light in a specific polarization. I don't know if it's vertical or horizontal, but just know that it's some fixed angle that the light will start traveling at. This Q switch, the so-called Optical cell, I should call it, what that actually does is it rotates the polarization of the light. So when you apply that high voltage, it's going to rotate it, gosh, I should know how many degrees. Let's say 45 degrees. I'm not sure if that's correct, so someone can correct me on that. Maybe 90 degrees. I should know this, but anyways, it applies some sort of rotation. And so what we're actually doing is we are basically polarizing the light, and we're making it so when the light comes back, it's at the wrong polarization and initially bounces off the filter on the way back. So based on whether it's at the correct polarization, we can control whether the laser starts gaining and increasing in energy. Does that make sense, roughly?
Yep.
Okay, so the other part of that, and this is where things get a little bit crazy, and I don't have a good understanding of optics to really understand this. So there's a critical piece over here called a quarter wave plate, and that's probably going to be really difficult to see on the camera. Maybe you can see it. There's a little wheel that's just to the side, kind of where my finger is. Maybe I can get a little pointy something to just be really specific. Oops. So this guy right here, if you can see that little wheel there, so that is called a quarter wave plate. And what that does, at least as I understand it, it does this magical thing where it will rotate the light, and it's designed very specially so that even if you're going this way or you're going this way, it's going to rotate the light in the same direction. And the reason why I say this is magic to me, because I was always taught that optics are very linear. If you do something this way, it's going to do the opposite thing, if you go back the other way. But no matter which direction you come from, it'll always say rotate it clockwise relative to the same direction. And to me, that's a little bit magical. So I don't claim to understand how that bit works. So,
and that's just some optical equipment, or is it actually there's electrified?
No, it's passive. So that's a crystal. Gosh, I couldn't say exactly, but some sort of polarization magic crystal. And I will leave it to the optics experts to describe the underlying physics. But the reason why this is important is because if we have this thing in here with this, these two can cancel each other out if they're not in the right configuration. So as we start aligning this, we have to be very careful to kind of understand the relationship between how this rotates polarization and how this rotates polarization and how this filters polarization. So this is all about making sure all those polarizations either completely cancel out when we don't want the laser to fire, or they all completely line up when we do want the laser to fire. Does that make sense?
Yep.
Okay. So with that in mind, the next question is, so the main failure of these lasers turns out to be that this element right here, the so-called Optical cell, those seem to either fail or this whole cavity as a whole gets misaligned. In my laser, for example, this is my old laser right here. This thing had a failure on a gasket, and I'm jokingly calling it the headlight fluid leaked out of the laser. So when you want a really clear optical surface, you may put something called immersion fluid in there. And what that does is it goes between two optics and makes it so it's optically clear between them, so you don't have any boundaries. Because anytime you have a boundary in an optical system, you can have a reflection, right?
Or refraction, I guess.
Yeah, exactly. Some sort of interference. We need that to be really clean. I think the issue is that the core crystal that's used in these are maybe really difficult to polish or something like that. So to work around that, they sandwich it between two other optics, and they fill the intermediate with fluid. So the fluid leaked out of this, and it had to be replaced. Here's the issue, though. The alignment of all of these optics together is extremely sensitive. So when we lost that and had to put a new one in, this laser no longer functions at all.
Okay, and that's the fix you did or are planning to do?
That's right, yeah. So I should also say as a high-level thing, I had two of these units. One of them was on loan, and I fixed the unit that was on loan. So now this is my actual unit, And the idea is to take the knowledge that I got from getting some help from someone who's a laser expert. He walked me through the procedure, how to fix the loaner unit. And now what I'm doing is I'm applying the knowledge from fixing that loaner unit to fix my original unit. Roughly speaking, that's kind of the idea. And
Great.
yeah, and so now the idea is if we were to just replace this one element, it's going to knock everything out of alignment. And there are so many optics in here that need to be aligned. It's going to be very hard to get everything, starting from that point back to a working state. So it turns out to be easier to do. Remember I said that we could operate this as just a very long, pulse. So, just it's the flash lamp is not being switched. It fires, the laser starts gaining, it outputs some light, you get a very long pulse. Do you remember we kind of talked about that earlier?
Yeah.
So the idea is just remove all of this stuff in here that you don't need initially, and just get the laser cavity firing in that very simple state. And that gives us at least a basic alignment. And then what happens is every time we add a new optical element to the system, it very slightly distorts the beam path. And then we can correct the beam path after adding that new element. And you iteratively just keep adding new elements until you get the laser fully working again.
And how do you measure beam path?
Great question. So this is the basic principle we're going to use. So you take another laser, because laser, you never have too many lasers. And what you do, this is the core bit, is you glue this to this adjustable mirror mount over here. And what that's going to let me do is do kind of a tip tilt as I adjust these thumb screws here. And what I'm going to do is start out by pointing this laser into the bore over here. And I'm going to measure the reflected beam coming back from this to this optic right here. And I'm going to assume that this optic is perfectly aligned with this bit of the laser here, because that tends to be a fairly good assumption that factory alignment is at least decent. And it turns out you can have a slight misalignment on these laser rods, and it's not a big deal. So as long as you align everything to this optic here, everything else can be aligned to it. So start by firing this fairly high power laser. This is a 100 milliwatt green laser, and shooting at this optic here and making sure it exactly bounces back into the laser over here, like to a very, very precise degree.
And how do you actually do that measurement? How do you know it's bouncing back exactly?
Yeah, so the basic idea, the way we did it, was we took a card, and in fact, this was a really interesting bit, and I wish I had this set up here. So as you're doing this, well, let me talk about the high-level idea. High-level idea is you just take a card, and you just look to see, is there a return beam that's not lined up with the other beam? So if you see another beam coming back that's not this original beam, you'll just see it indicated as you put an object in the way, and you know.
Okay. So you do it visually, actually.
That's right, yeah. So that's actually a great segment. So originally, I was told that the proper way to do this was using something called an autocollimator, which I'm probably pronouncing wrong. I usually pronounce that wrong, which is like a very factory, like precise way to do it. But unless you're doing something at scale, and by the way, that does essentially the same thing, just with like AI and a camera or something like that, some sort of machine vision. Unless you're doing this at scale, it's better to do this all by hand. It's just not worth the automation and setting all that stuff up. So the other interesting bit is, though, we're wearing these laser safety goggles because a lot of this is pretty high power, and ideally you don't want to be exposed to it. My friend had these special cards that would basically convert infrared light, some of it's leaking out of this laser and the other laser over there, and it would convert that light into orange light that was not blocked by the laser safety goggles. And so by doing this conversion process, we were able to get a small amount of test light that could be seen through the laser goggles but not be hazardous. I thought that was really interesting.
And you said, so you're using a couple of different lasers, right? On the topic of safety, those goggles protect you from both types?
Yeah, so this one right here is only green. So this is maybe not the best example. I have another pair that's this brighter spectrum. So all goggles, if you can read that, I don't know how well.
No, it's blurry. We can't read it.
Okay. So all goggles have the so-called OD rating, the optical density, and that indicates what wavelengths they will protect you from and how much. And ideally, what you want to do, at least in my opinion, is you want to attenuate the beam to the point where it kind of looks like a laser pointer or something harmless like that. So it's not so much that all the light is blocked and you don't know where the laser is anymore. Because, especially as it's a high power laser like this one, I haven't actually shot myself with this laser yet, but given how much of a crater it leaves in everything else that it touches, I probably wouldn't want to get shot by it. So, let alone your eye, but yeah, you want to have some visibility. Does that make sense?
Yep.
Okay. So you have a basic idea now of roughly how the laser works and how we do this very first alignment from this laser to this mirror, right?
Yes.
Okay. So now what we're going to do is we're going to also rip everything else out over here. And the reason why we're using a relatively high power laser, this is like 100 milliwatts, is because what we want to get is a very small reflection that comes off of this mirror, goes all the way back, and comes back over here. And the reason for that then is we know what the relationship between this mirror's reflection is and this one. So there'll be a first reflection from this mirror and a second reflection from this mirror. And by lining, this laser up to the reflection from this mirror and the reflection from this mirror, we will now have all three of these in perfect optical alignment. Does that make sense?
Yeah, that sounds pretty cool.
Okay, so once we do that, at that point, we should be able to fire this laser and we'll get the long pulse. So it won't make like a satisfying snap like the really quick laser does, as it just completely obliterates things. But you should be able to, put a piece of paper in front or something, and it'll punch through that, it'll set things on fire. And at that point, you're good because this flash lamp is working, this high voltage is working here. You're in a pretty good state if you manage to get it that far. So that's a good starting point. Now, from there, though, the next thing I think I did was we put in this so-called Brewster angle, optic right there. And that's going to start adding in the polarization because that's still a fairly safe operation. Because all we're going now from a laser that just kind of randomly polarized the light to something that's just going to slightly polarize the light. And at that point, what we're going to do is this is going to knock it slightly out of alignment once again. But at this point, we're done with this laser here. What we're going to do is we're going to switch from this guy, which gave us our coarse alignment, to something which is going to give us our fine alignment. And this is the one specialty-ish sort of tool, which I fortunately got on loan from someone and didn't have to buy. We have this very fancy, if I can get this on camera, I'm going to have to pan a bit. Give me a second. Oh yeah, new camera setup, very fancy. So what I have here is a professional laser power meter. And so there is a sensor here, which gets hit with a high power laser pulse. And this meter here is able to read out how much laser was absorbed and energy was absorbed in that pulse. So what we're going to do is we're going to keep shooting the laser with this. And we're going to very carefully adjust the mirrors on the laser and look to see whether we're getting higher or lower power. And it's basically just a simple optimization problem to just tune the X and the Y until you get the highest laser power.
Sounds good. And these are just, like little knobs you rotate.
Yeah, so let me see if I can get a close up on that. I'm going to take this off. So more specifically, if I can get over here. So you see that socket head cap screw up there with a red on it?
Yep.
So there's two of them there. And actually, those may not be the right ones. Let me actually get you the right ones here. And give me a second. I'm going to try to rotate again. Stand by. Okay. So there's the red one on top. That's actually a clamp, which holds this in place so it doesn't get out of alignment. There's a very small one here. So you see this one right here?
Yes.
So that's the one that actually does the alignment. This one just clamps this one in place. And you can see there's another pair over here. Hopefully there's one down there, which does the actual alignment. So this is the X1 here, and this is the Y1 over here. And there's a spring, so these are springs over here. And this is a so-called kinematic mirror mount we're looking at.
And are all your alignment isolated to just that plate there, or do you have to align a bunch of stuff in between as well?
So we're basically doing is we're primarily going to correct the misalignment in the other parts by making alignments in this part. So yes, it is possible that we might be able to correct in other areas, and we will do that for some fine tuning, but at least the gross alignment will be corrected over here. Make sense?
Yep, sounds good.
Yeah. So with that in mind, what we're going to do, let me get this set up back over here, if I can. Oops. It's behaving. Okay, I think we have that mounted, and I am going to swivel back over. Okay, I think that's roughly where we were before. All right, so now that we have kind of a rough idea of what the laser alignment is, we put in this polarization, the next thing to do is to put, remember I said we took all the stuff out? We're going to put this quarter wave plate back in, but we're going to put it in initially, not at the final configuration, but something that's going to rotate the polarization back such that we actually make it through that Brewster plate. So there's these very fine pin, basically adjustments you can make by rotating it. And we're going to put this in, and then we're going to rotate it until the laser starts firing again. And that means that it's passing light enough to polarize in the way that we get light out of the laser. So basically just kind of cancel itself out, so to speak. Okay?
Mm-hmm.
So by rotating it that way, and then after inserting this, we will make the XY adjustments here to then optimize the laser power after that. We're able to correct the aberrations that this polarization plate introduced into the beam, and then get it realigned to the beam path.
Okay.
Does that make sense?
Yeah.
Am I losing you?
No, I'm with you. It's interesting stuff. I'm just really focused.
Okay. I need to get you laughing a bit more. Look really serious.
But I'm pumped.
Yeah. Well, we're almost done in any case. So the last, there's 1 or 2 steps left, basically. So now we insert this Optical cell back in here, which is also going to, gosh, I can't remember, and if it's passive state. I think if you just insert it with the polarization like we have it, the laser will actually fire. Because I think when this thing is off, it doesn't do anything. So we'll insert this optical switch back in, and we'll just realign this XY, just like we did before. And we may also do an iterative process where we might adjust this position slightly and then have to realign, but just kind of iteratively jiggle the optics until the power is good. And then we're almost done, because at this point we have the optical switch installed, but it's idle. And we have the quarter wave plate installed, which is rotating the polarization, but they're set up right now so they essentially cancel out. So the last thing we need to do is we will rotate this, gosh, this is like 45 or 90 degrees. I don't remember off the top of my head. But basically, you're going to rotate it so that this will actually block the light initially because it will beat the wrong polarization. But then this Optical cell will rotate the light. And due to that rotation being lined up with this quarter wave plate, it'll suddenly switch the light when the laser fires. And you'll get one high power pulse coming out of the laser. And at that point, the laser is in its full power once you've done a little bit more adjusting tuning. But you have all the components back in. It's firing at a very short high power pulse. And that's how we brought back the other laser from the dead.
Very cool. And how long did this whole thing take to just the adjustments?
Well, I mean, we were also figuring this out because we had never really, done this sort of thing before. I think that took us on the order of magnitude. Once we had a plan, I think it took us maybe 4 hours, maybe to run through that procedure. I think if we did it again, it would be less than that. But yeah, on that order of magnitude, because there's so much tuning, integration testing with a microscope. And one of the things I've glossed over, although it's not so bad, is if you look, this is the main laser cavity. But do you see this whole mess of things over here?
Yeah.
So that's the primary laser on the left, but it also goes through all of those optics on the right. So once we get that main laser set up, we also have to do more processing to realign everything on the right. Although The right is not as bad as the left. Honestly, the left is a lot harder. Like I knew how to fix the stuff on the right. I didn't know how to fix the thing on the left because it's way more sensitive.
Okay.
Yeah. So there you have it. I would say that's kind of the core of it. So hopefully we still have some people with us. Were there any YouTube questions, anything like that?
No questions yet, but people are still with us, so I think they enjoyed it. It definitely was. It's definitely interesting, and I think there's a whole bunch of stuff we can touch along the way, like in future episodes. I think I have a few questions as well, but they're I think for longer form questions.
Yes. So I think that was as high level as maybe we could go for this video. I don't know if you have any more questions or if anyone else has questions. Otherwise, this may be a good point.
I do have actually one question,
Okay.
and I don't know if you know it, or maybe you can ask your friend who's the professional laser guy.
Yeah.
So with alignment being such a big deal, why don't they, or maybe they can't do that, maybe that's the inherent issue, is like when they build these little Pockle switches or these optical things, like if they factory align it to like physical kind of enclosures, and then if you have like very high tolerance kind of guides, you can just like slip them in, or they just happen to go out of alignment naturally over time.
Yeah. So there's a number of issues. A good example is, my microscope just broke. So let's just take that as an example. So the precision on that microscope, I need to keep something within a micrometer of focus, sometimes over, 24 hours on an area of like, 10 by 10 millimeters. So if you think about like the precision requirements of that, that's relatively high. And so it turned out why the microscope failed recently was because I made that setup maybe 10-ish years ago, 8 years ago. Over time, a screw had basically come loose, due to a lot of the vibration of the stages moving around. And it had very slowly destroyed the threads on the microscope so that it didn't fall apart, but the screw wasn't as tight. And, it's really hard to defend against those sort of long-term effects where a screw over 10 years comes loose. And I think that's a lot of what we're seeing on this microscope is, there's fans running and, other stuff, and they try to avoid that. But over long periods of time, glue comes undone, screws move, and the precision is just so high that it's hard to keep it in alignment for that period of time. As far as, slipping in a new module, yes, you might be able to slip in that whole module, but that's going to be very expensive, and you basically total the laser at that point. We just happened to have a source for the replacement optical switches. And with the knowledge of how to install the switches and just a general interest of learning more about optics, in this particular case, it definitely made more sense just to replace that one switch.
No, very cool, very cool. Yeah, I mean, hey, thanks a lot for this. Was very informative, and hopefully we'll, if viewers are interested, send us comments, and we'll cover a lot more laser topics in the future.
Sounds good. All right. Well, thanks, Ewan, for watching then, and until next time.
Thanks. Bye.